Hello everyone. In this lecture, we will continue the study constructing a flow in the network for digraphs and some criterion to get the maximum flow. So first we define the following set. So for each set of vertices, U, let probably I should say each subset, let U right arrow to be all edges whose initial vertex is in U, but the terminal vertex is outside U. Correspondingly, we can define U left arrow to be edges whose initial vertex is outside U, but the terminal vertex is in U. So if you draw a picture, there will be, so suppose this is U, and then those will be in U right arrow, and sorry. Those will be U left arrow. Okay, and then we have the following lemma. Let F be a flow in the network, the special network, the network for digraph n equals VA ST omega, and U is a subset of V containing S but not T. Then the summation of the weight for edges leaving U minus the weight entering U is the same as the weight whose initial vertex is S minus the weight whose terminal vertex is S. And if we consider the picture, it will be quite obvious. So suppose here you have a source, and then for the source you have flow lines in and something out. Okay, so the red part corresponds to this one. The blue part corresponds to distance, and then outside we have the similar thing. So this is leaving U, so this corresponds to distance, and entering U, so this corresponds to this one. And in a short word, why this theorem is true? Because you only have one source. All the other points the flow in and flow out cancels each other or equal to each other. And the proof also follows from that idea. So we evaluate the sum equals x f alpha minus tau alpha equals x f alpha in two different ways. So on the one hand, it follows from the definition of a flow that all terms in the outsum are 0 except for the one corresponding to the vertex S. Hence, the value is summation L alpha equals S F alpha minus summation tau alpha equals S F alpha. Okay, then on the other hand, the star equals summation x in U L alpha equals x F alpha minus x in U tau alpha equals x F alpha, or equivalently summation L alpha in U F alpha minus tau alpha in U F alpha. Notice that it's still a little bit far away from the quantity we want, because the quantity we want is U left arrow or U right arrow. In other words, you want the edge leaving or entering U. So to derive this, we noted that each arc alpha with both its initial and terminal vertices in U makes a net contribution of 0 to the summation star. Therefore, after this observation, star equals alpha in U right arrow F alpha minus alpha in U left arrow F alpha. So we are done. A small remark is if we take U to be V minus the target T, then U right arrow is the set consisting of all edges whose terminal vertex is T, and the U left arrow is edges whose is a set of consisting of edges whose initial vertex is T, and therefore the above lemma, we can conclude the following by the above lemma. So summation of F alpha for all L alpha equal S minus summation of F alpha for all tau alpha equals S equals summation of alpha F alpha tau alpha equals T minus F alpha L alpha equals T. Actually, this is the formula we derived a long time ago in the last lecture. And we will call this quantity the value of the flow F, or denoted by VLOF. Okay, when we have some objects, we always want to ask what is extremal case. So in this situation, so given a network n equals VAST omega, a flow in n is a maximal flow. Provided that it has the largest value among all flows in n. And then the value of a maximum flow equals the minimum value of another quantity. So in the following, we will illustrate what is this quantity. Okay, and so we introduce another notation, a cut. So a cut in a network n equals VAST omega is a set C of arcs such that each path from the source S to the target T contains at least one arc in C, and then the weight omega. Recall that the weight of a subset of edges is the summation of the weight of each edge in that subset. The weight omega C of a cut C is the sum of the weights of the arcs in C, and a cut is a minimal cut provided that it has the smallest weight among all cuts in N. And a cut is a minimal cut provided that each set obtained from C by deletion O1O, its arcs is not an arc. So in reality, we will use the following version. So minimum means for each arc in C, there is a path from S to T that contains there's path alpha from S to T that contains alpha but no other arc of C. Okay. Actually, I leave this to you to verify this. You can verify this by contradiction. This criterion is very useful. And also, I would like to make two remarks. So first one, minimum cut must be minimal. And secondly, what's the difference? If I draw a picture, probably you can have some feeling. So these two can be viewed as minimal because locally, by deleting one arc, you cannot get a smaller cut. But then only this one is minimal. Because for a minimum cut, you need to compare the exact value of the weight. Okay, and then even so for this one, although it's local minimum, but when you compare the weight, it's not minimum. So it's not exactly in this form, but you can understand in this way. Okay. And actually, the idea for introducing minimal cut is that it's similar to the case when we do calculus 1. So for the global minimum, usually you do the derivative test to find all the local minimums and then evaluate the value at those points and then pick out the smallest one or largest one. So the same thing here. The global minimum is very hard to control, but the local minimum is relatively easy. So in the following, we first show that any minimal cut can be characterized by the leaving set. So it's a cut of the form you right arrow for some set of vertices U containing S but not T. And then this implies that the smallest weight of a cut must be achieved by a cut of this form. This form means the leaving set U, right arrow. Okay, lemma. So we first state the following lemma. Let N be a network with C a minimal cut. Let U be the set of all vertices X for which there exists a path from the source S to X that contains no arc in C. Then U right arrow is a cut, and C is U at arrow. So if you draw a picture, of course here the theorem is true only if C is a minimal cut. In other words, there's no redundancy. So the idea is, suppose you have C, which is a cut, and then from S, you look for all the possible points, and then eventually you will have a set U. Okay, then for a set U, you might have some some leaving set, you right arrow, so you conclude C is just this one. So T is here, T is here. So you have another part. Okay, so graphically we have this situation. Okay, now let's prove this. Note that S is in U for the trivial path gamma U contains no arc in C. Okay, also since C is a cut, the target T is not in U. Otherwise, from S to T, there's a path without any edges in C. So it's a contradiction. Okay, and therefore, hence, your right arrow is a cut. This is not trivial. You need to argue a little bit, but it's still very easy. Because any path from S to T has an arc x, y, such that x is in U, but y is outside U. This is due to the fact is T is outside U. Okay, so you can always have one arc satisfy this quantity, then this arc is in U hat, U red arrow. Okay, next, each arc xy in U hat is in C. For otherwise, there is a path from S to Y containing no arc in C, and Y would be in U, which is a contradiction. So here, it's also not so trivial. So why there's a path from S to T containing no arcs in C? Because there is a path from S to X without any arcs in C. This is by the definition of the set U. And then xy is an arc not in C. Then adjoining these two, we have the path from S to Y satisfy such property. Okay. So from this, we can conclude that. So here is very important. Property. The set U red arrow is a subset of S. Okay, and from the statement in the lemma or in the theorem, we need to verify the opposite direction. So now let alpha be an arc in C, since C is a minimal cut. There is a path gamma from S to T that contains alpha but no other arc of C. And this implies that the initial vertex A of alpha is in U. So this is because if there were a path sorry. So this is the easy part. The alpha A must be in U, and then we need to show that B is not in U. So if there were a path gamma prime from S to B that contains no arc in C. Actually, why A is in U, I leave it to you. It's clear from the path gamma we chose. Okay, suppose there's gamma prime from S to B that contains no arcs in C. Then gamma prime followed by the part of gamma from B to T would give a path from S to T containing no arc in C. So if you draw a picture, this is the part C, and you have alpha here, and from S to T, we will have only one arc alpha in C. Okay, so this is A, this is B. So if you have a path gamma prime from S to B without any arcs in C, then we consider the green part with the pink part. That will give us a path from S to T without any arcs in C. Okay, so that would be a contradiction because we assume C is a cut. This is a contradiction. So therefore, there's no path from S to B without any arcs in C, and B is not in U. So thus, alpha is in U right arrow, and hence C is contained in the set U right arrow. And to conclude the property that U arrow is in C, then we complete the proof of the lemma. Okay, now we can state the main theory. So let M be a network then the maximal value of a flow in N equals the minimum weight of a cut in N. So moreover, if weights of all arcs are integers, then there is a maximal flow, all of whose values are integers as well. So proof, we first show that for each flow F and each cut C, value of F less than or equal to weight of C. So by lemma in the above, it suffices to prove star for cuts of the form U right arrow, where U is a set of vertices with S in it and T is outside it. And this is because value F is by the lemma before the previous lemma, we have value f is the summation of f alpha for all alpha leaving u minus f alpha for all alpha entering u. And by the definition, f is non-negative. Therefore, you can drop the second part in the equality. Therefore, we have this is less than or equal to summation of alpha for all alpha leaving u. And of course, because f alpha is less than omega alpha, we have this, and the last quantity just weight of the set u right arrow. Okay, then we are going to prove the other direction. But to prove it, next we assume that the weights are integers. So this is just for the technical reason. So when we done the case in which weights are integers, we can easily generalize it to the rational valued weights, and then take a limit. We can derive the case when weights are real numbers. But those tedious limit process we will omit here, since some of you are not so familiar with Math 2021 materials. But the idea is rational valued case follows, and then taking limit, we can derive the real case. So for why this real rational follows, because we can multiply a very large number n to all the weights, and so that those weights are integers. Okay, and after we have the corresponding flow, we divide the flow by n at the end. Then we go back to return to the original case. So we will not bother with the limiting process. Okay, next. We are going to show that there is a flow f hat with only integer values and a cut c hat such that value f hat equals weight of c hat, and then by star such a flow f hat is a maximal flow, and the cut c hat is a minimal cut. So I leave this to you. Why this is true? It's not that trivial. If you understand this actually in Math 521 real analysis, mathematical analysis, you understand why the infimum of the supremum is greater than the supremum of the infimum. Okay. So to do this, we start with an arbitrary integer valued flow f on n. For instance, we can choose the null flow, zero flow suffices. But in reality, of course, you can choose better initial data. We can find more reasonable initial flow. This is a zeroth order approximation. And if you are in computational mathematics, a very important issue for some algorithm is you need to choose some good initial data to start with. So some bad data will lead you to some unstable phase. Okay, then So to do this, we introduce the following algorithm. We then describe an algorithm that results in one of the following two properties or possibilities. So one is called breakthrough. In other words, you improve the flow a little bit. An integer valued flow f hat has been found with value f hat equals value f plus 1. Okay, if this happens, we repeat the algorithm with f equals f hat. Okay, and then the second case is non-breakthrough. So no such f. Then we show that there exists a cut C hat whose weight equals the value of the flow. And then C hat F is our desired object. Okay, and then the basic flow algorithm is as follows. We begin with an integer valued flow f on the network n equals v a s t omega. And step 0, set u to be a set consisting of s. Step 1, while there exists an arc alpha equals xy with either x in u, y not in u, and f alpha less than omega alpha, or x not in u, y in u, and f alpha greater than 0, put y in u in case A, or put x in u in case B to output U. So to summarize the idea in the first step, we can use the following idea. We seek an arc in U in leaving set whose flow value is less than its weight. And then put in this arc, update U. And B, an arc in entering set with positive flow value. Okay, then put in this arc, update U. And why we want to do this? Because if we look at the inequality we used before, we will drop the second quantity and maximize the first quantity. With omega alpha in U hat minus 0. Okay, so here we want to approximate the left-hand side by the right-hand side. In other words, we want to maximize the left-hand side and then minimize the second quantity in the right-hand side, so that this is equal sign. So this is the idea. And the method used here, actually, if you look at it, can be described by porous media model. You can search on Wikipedia what does porous media mean. And actually, there's a very active subfield in the boundary of mathematics, probability, statistics, and physics, which is called the statistic mechanics with mathematical method. So they study the phase transition of some porous media model. And in those models, there will be some parameters, for example, mu. And with mu less than 1, so we will see in our case that S and T cannot be connected. And then when mu equals 1, so will be random graph. And when mu greater than 1, for instance, there will be a path from S to T. Okay, just like the flow can flow from S to T. Okay, so then the mu equals 1 is a critical point, and which has conformal symmetry by the theorem from statistic mechanics. So this is a very interesting field. If you are interested, you can look at that. And the computer science can also enter in, because sometimes you need to do some simulation and do some computation. Okay, and we will not talk too much about this. Let's go back to our theorem. So after the algorithm stop, we have two cases. First, T is in U, and then it follows from the algorithm that, recall that every time you enlarge a set U by one vertex. Okay, so therefore, you can find, if T is in U, so we can find a sequence of integers satisfy the following property. There is a sequence of distinct vertices x0 equals s, x1, x2, xm minus 1, xm equals t, such that for each j equals 1, 2, 0, 1, 2, m minus 1, either a alpha j equals xj, xj plus 1 is an arc with f alpha j less than omega alpha j, or b alpha j is xj plus 1 xj, so the arrow is reversed, is an arc with f alpha j greater than 0. Okay, then define. Recall that although we find some imperfect in the original set flow, we have set U, but then to modify it, to get a new flow, we need to satisfy certain properties. It's not trivial, just change one arc. The value at one arc is not enough. We will see from the argument underneath. So define alpha prime to be an integer valued flow by the following formula: f alpha plus 1 if alpha is one of the arcs in A, f alpha minus 1 if alpha is one of the arcs in B, and otherwise f alpha otherwise. Okay, and we can see in this case f prime is strictly okay. So we need to check the following property. So check f hat is a flow. So first, the value of the flow should be between 0 and omega alpha. So this is true because every time when we increase the value or decrease the value, we always have the value is between 1 and omega alpha minus 1. So after change, we still have this inequality. And secondly, we need to show that if the vertex is not S, neither T, then flow in and flow out should be the same. So this is kind of a little bit complicated than we thought. We have 3 cases actually. Let's focus on xj plus 1. Okay, and then we have 3 cases. X so right, left, and left. Oh, actually we have another one. Right. Oh, sorry, left, right. And we need to verify the statement 2 for each case. So for the first one, we have the difference for the flow f prime, because we only change the xj blah blah whatever. So here, and also x0 to xm are distinct, so we can rewrite this as difference between flow in, flow out for flow f, and plus f prime xj plus 1 xj plus 2 minus f xj plus 1 xj plus 2 minus f prime xj xj plus 1 minus f xj xj plus 1. Okay, so this is correspond to the change from f to f prime, and then this is 0 because f is a flow. And for the green box, it's easy to see. We have 1 minus 1, which is 0. Okay, so let's give them some indices. And then for 2, everything is similar. Except when we do the correction, we have different signs because we have different modification. So here you have minus f prime xj plus 2 xj plus 1 minus f xj plus 2 xj plus 1 minus f prime xj xj plus 1 minus f xj xj plus 1. So this is minus -1 minus 1, which is 0 as well. Okay, and then for 3, we have plus f prime xj plus 1 xj minus f xj plus 1 xj minus f prime xj plus 2 xj plus 1 minus f xj plus 2 xj plus 1. And this is -1 minus -1, which is 0. Okay, and then for the last one, we have blah blah f xj plus 1 xj minus f xj plus 1 xj and plus f xj plus 1 f prime xj plus 2 minus f xj plus 1 xj plus 2. And then you have the first one is -1 and second one is +1. Okay, after all, we prove that f prime is a flow. And then if we calculate the volume of f prime, then it's easy to see volume of f prime is volume of f plus 1. So I leave this to you to verify this. Okay, and then for case 2, T is outside U. Then in this case, leaving set U right arrow is a cut, and it follows from the algorithm because you cannot do any improvement anymore. Therefore, f alpha is omega alpha for all alpha in U, leaving in U a red arrow, and f alpha is 0 for all alpha in U left arrow. Hence, when we calculate value of f, we have the extremal case. This is the weight of alpha for all alpha in the leaving set. Okay, then we are done. The U hat F is what we want. Okay, so next we are going to give some more geometric explanation of the proof in the above in certain simple case. Actually, yeah, I will tell you later that there's a very strong geometric flavor underneath the proof or underneath the theorem. So let D be a digraph that models a communication network, and then the vertices represent junctions, and the arcs represent one-way direct lines of communication, and fixed S and T, fixed junctions S and T. How to establish a communication path from S to T with least lines with fewest lines. And in reality, we will also have the problem that sometimes the connection may fail. Then you need to have some redundancy to make sure the communication still work. Lines may fail. It's important to have redundancy in the digraph. And we define an ST separating set. This is probably the terminology in the information theory, set to be a set S of X of D such that every path from S to T uses at least one arc in S. And in engineering, so probably people will have an eye on the set separating set. When they find all the lines in this set are broken, then they will take steps to fix it. Because from the definition, whenever those lines are broken, the communication is stopped. Okay, and we have the following theorem, which is a direct corollary of the above theorem. So the maximal number of pairwise arc disjoint paths from S to T equals the minimal number of arcs in an ST separating set. So the proof, let VAST omega be a network with weight constant function 1. And a cut in N is an ST separating set in D, and vice versa. Okay, then we just have the previous theorem, and also recall that the weight of a cut equals the number of arcs of the cut. Okay, then consider an integer valued flow f in N, and let value of f to be p. Since omega constant 1, f takes 0 or 1. So either chooses alpha if it's 1, or not if it's 0. So we prove by an induction on P that exists P pairwise arc disjoint paths from S to T made up of arcs chosen by F. So if P is 0, it's trivial. Assume P is at least 1, then there's a path gamma from S to T. Otherwise, this is true. Otherwise, if there's no such path, if U is a set of vertices that can be reached from S by a path, then leaving set is empty. And moreover, here empty set is the leaving set is a cut in N with weight 0, contradicting P is greater than or equal to 1. So why this is a cut? Because deleting the leaving set, there is no path from S to T. Okay, then let f prime be the integer flow of value p minus 1 obtained from f by reducing by 1 the values of the flow on the arcs of gamma, and then by induction there exists p minus 1 pairwise arc disjoint arcs from S to T. Oh, so sorry here. Paths S to T made up of arcs chosen by f prime, and this p minus 1 paths together with f are p pairwise arc disjoint paths made up of arcs chosen from f. Okay. So here actually you need to show that it's not hard, but you need to show that in order to apply the induction, the volume of f prime is p minus 1. Okay, then conversely, if there's p pairwise arc disjoint paths from S to T, then there is an integer flow in N with value P. Then by the previous theorem, we can complete the proof. And the reason to introduce this theorem is only because I want to draw the following picture. So you have flow lines. Also some broken one. And this is a cut. Okay, and those are flow lines. So the weight of the cut is the same as the number of flow lines from S to T, or called disjoint. Okay, and equals the value of the flow. Or probably it's better, better to combine something here. Okay, and so if we turn back to the previous theorem, then we can also draw a similar picture. That is, how to estimate the value of a flow. We only need to look at the thinnest part of the network. So this is a cut. This is a neck. Okay, thinnest. So the volume of flow is less than or equal to the weight of the cut. So from this picture, you can easily imagine what does the theorem mean. Okay, so the theorem actually constructs the best case that if the thinnest part, for example, is P, then you can always find P long lines from S to T. So they are disjoint. Okay, so I will stop here. Next time we will turn to chromatic numbers.